Let's start. The first question that I want to answer today is this one. Just a minute. There are some unwanted things got opened. Let me, yeah. So one question that come from your one of your classmate, that why suddenly here we could write that this becomes 0.5. What was our pi d by p? That becomes 0.5, right? See here, one information is given, pole pitch is 0.5 meter. But we need to understand what does that mean. Let me explain to you with this one. See, this is the diagram of the structure which I used to demonstrate. Now, suppose you have four poles. Therefore, you can assume that here you can broadly broadly like divide this into 2 to 4 quadrant. So 4 quadrant, 4 pole. If you find this looks odd, then let me draw some nice lines. Like here you have n is n is like this. Well, now what gives me my pi d? If I take pi d, then that pi d means this if I make a complete transition from this point and again return to this point along the periphery of my armature, cylindrical armature, then the total length of traversal will become pi d. Now, if I have, say, 4 poles, then this should be divided by pi d by 4. So, precisely this length, this amount of length is something that is pi d by 4 in this curvilinear path. So this pi d by 4 is actually the length which is given by one pole pitch. One pole pitch means your if you consider the cylinder and go for its surface development. So suppose you have a cylinder like this. Right, and then you go for surface development. Let me draw it in this side. So after surface development, it will look like this. This entire length will be how much? Pi d, because d is the diameter of my bore. So pi d is the total length. And in this manner, we can see that the pole, any one pole, if it is 4 pole, we can divide this in 4 symmetrical segments, and every one will denote one pole pitch. Therefore, the question which he asked, that pole pitch 0.5 mm implies when you have this pi d by p, you should replace that by 0.5 mm. Typically, pole pitch is given in terms of length. And if you try to find out the area covered by each of the pole, then you just need to multiply the length of the cylindrical axial length of the cylinder, and that will give you like this. This is the total area of one pole. Once you have that, how much area is coming under one pole, then what you can do, you can think about what is your B1, or precisely how this B is calculated. This B is the fundamental value of flux density. Now, fundamental means here, to be more precise, this gives you the magnitude of the fundamental value. So, when we are talking about B1, so let me just take you here. Well, all right. Let us take this. This is the just give me a minute to open another file. I'm sorry for this means trouble. Just it will take a few minutes and then we can roll. Yeah. So in the given question, we are supposed to use this formula. Right. Let me take you there. That I'm talking about this. The same thing here we are having, since we are considering fundamental, so it is 1. So that gives you the fundamental MMA. Right. If you multiply it with mu, you will get B. But that's not my major concern. What is there? That the same formula, okay, and here everything is in terms of flux. So what you can find out, what does this, since I'm discussing on this topic, just let me tell you, this BM indicates this much. This is my BM, correct? So the formula for fundamental becomes cosine epsilon. And since all the things are in terms of B, so we can just replace this A, which was denoting the MMA, by B, which will now denote the flux density variation. So we got our B1. But what is that B1? Precisely, we should write B1 in. Using this formula, we are actually getting this value. Correct. So once you find this B1M, what is your objective? You have to find out the average flux. So what we know, this entire region this entire area under this curve, we can find out if we know the average area. So how much is the average flux? Since this sinusoidal, this fundamental is sinusoidal, therefore we can write this average value is once we find out the average value, then what does that mean? That means this average value of flux is available for the total loop. Now, what is the amount of traversal you are traveling here in this way? This amount is pi d by p, your one pole pitch precisely. And when you multiply this pi d by p into L, that gives you the area. And now you already have our B1 average. So when you multiply them all together, they gives you the total flux per pole, right? So I hope now with this explanation, the formula should be clearly understandable to you. If you further have any doubt, you can ask me about the same, right? Now, just give me a minute. Let me check whether it is audible or not. So let us start with this problem number 11. I think I discussed problem number 10 the last day. So let us discuss problem number 11. So what is there in problem number 11? Problem number 11 asks 6-pole synchronous machine has a rotor winding with a total of this much series turn and a winding factor this. The rotor length is this much. The rotor radius is this much. The air gap length. What is the rotor operating speed in R per minute? All these things have been asked. Okay. So we have to answer all these questions. Okay. Let us start with the basics. So 11, question number 11, a 6-pole 60 hertz synchronous machine. Here, first of all, we need to understand that the rotor winding with a total 138 series turns and a winding factor. The rotor length is this much. So what is the rated operating speed of rotor in R per minute? Means rotation per minute. So how can we find out? Let us go to our formula. Just a minute. Here, the formula is this. The air gap induced EMF formula is this one. Now, until unless specified, we'll always consider the basic, yeah, the basic fundamental MMF is only present. Now let us go back to the problem. What it says? It says 60 Hertz synchronous machine has a rotor winding of this. The rotor. Okay, one thing we can easily find out the radius per minute because 6-pole. So from that you can use this formula 120 F by P is equal to here it should be the rotation per minute. So 120 into 60 by 6. Therefore, perhaps you will get 1200 RPM. Correct. Now, here you have to find out calculate the rotor winding current required to achieve a peak in the fundamental air gap flux density of 1.23 V. So here you should apply the same formula that we discussed in this document 26. Today I may not be able to carry out all the calculation, but let me tell you. And once you use this formula, you are sure to get the correct answer. This is the formula for your rotor MMF. Provided here, we are assuming that this rotor is going to produce a kind of rectangular flux distribution. This is very important to understand how to select this formula. See here, the rotor is like this is kind of this formula we are using. See here, there are 3 rotor slot, the area and length, the number of turns in the each winding. Now, what is happening here, this case, you have the total ammeter loading given, that 1500 ampere turn per pole. And from that, you find out the breadth factor and all this. And then you proceeded to find out the total ampere turn per pole. Then you utilize this formula and then you got the result. Now, on the contrary, what you have here, you have these things given. So, what you should do, you should put here that in this formula 1.23. Correct? Because whatever you are getting, it's a peak. Right? The peak fundamental flux density is 1.23. Now that rotor radius, rotor length is given, and air gap length is 3.15 mm. So once you have 3.15 mm, here you should put that 3.15. Now, the other information that 1.97 and 58, that should be placed where? Here, to find out the total area. This one. Sorry, no, total area not written here. So now we are ready to find out the A1 M from this. So you have V1 M given. So V1 M into LG by mu naught gives you our A1 M, the air gap. Now, what it's we need to understand that here no information is given about the like what type of waveform will be produced by this one. So why this waveform is very important? See, if we look at here, if you have a square waveform for MMF, you get this. if you have a full, okay, if you have this one, your equation is slightly changed. So for a trapezoidal rotor MMF, you have a different equation. For a triangular rotor MMF, you have another equation. But until unless mentioned, what will assume that our waveform is having this kind of equation, or precisely we may take what I told you to take help of this generalized one, where you have this. The NP is equal to total number of turns per pole, and finally it gives you this formula. So if nothing is mentioned and winding is distributed, then probably most of the times you are going to get a staircase MMF waveform like this. So once this staircase MMF waveform is generated, then you can safely use this formula. Right. So what is that? You have your 1.88, sorry, 1.8. So let us put that too. You have your A1M coming from here. Now A1M is equal to 1.8 NP, that is total number of turns per pole. Here it is given somewhere 138 series turns with a total 138 series turns. So you should divide 138 by 6 to find out the one, probably 23rd to 23, which is coming in my calculation. So 1.8 into 23, then what you have, sorry, the formula here, that 23 into I, here we need to find out the I, and this one is given. So we have 23 into I divided by R into winding factor given 0.97. So from that you can find out the magnitude of I, which is asked here. So I could be find out in this way. Now we have to calculate the corresponding flux per pole. So in that case, you should take the from this A1M. Now here, be very careful. One thing you should understand, this A1M is something different from your this one. Right? This A. So here you should use this part. All of them are A by N rectangularly distributed, and you get this formula. Right. So your flux, when you should consider that the peak flux, from that you can calculate, just like the previous case, you can calculate the flux density, and from that you can figure out the total corresponding flux per pole. I do not know what happened, just a minute. Okay, so our 11 is solved. Now let us go to 12. Assume that phase winding of synchronous machine of problem 11 consists of full pitch 11 turn coil per pole pair with the coil assumed okay. Let me write down the answers. Here, this one is 1200. The second one should be I 1 is equal to so we have 113 ampere. Now the flux per pole here, if you follow the way I suggest you, according to my calculation, it is coming 0.937 Weber for this one. Right. Now what it says, assume that phase winding of the synchronous machine of problem 11 consists of one full pitch 11 turn coil per pole with coils connected in series to form the phase winding. If the machine is operating at rated speed and under the operating condition of problem 11, calculate the RMS generated phase voltage. So what you have for this one, you can write PRMS. What should be the proper formula for that? It should be coming from omega in into your phi. Now your phi P is flux per pole is 0.937 Weber. Therefore, what you can have here, this flux per pole you should use here, and you can use this formula. Right, 4.44 kBr kPr. Now kBr is kPr is full pitch. kVr, just let me check. 11 coil per pole pair. One full pitch coil. So there is nothing to find out. What you have here is really that you should find out the value using this formula 4.44 your kbr kpr you know 1 then your f should be the value 60 hertz. R is the order of harmonics, so R is 1. Now how much is your n? N is 11 coil per, and what is your phi flux per pole? Flux per pole is your, in this formula, flux per pole is which we got from the previous case, 0.937. So the total answer, if you evaluate, it will come around 8.24 kilovolt. Correct. Now, in the 13, the three-phase synchronous machines of problem 11 is to be moved to an application which requires the operating frequency to be reduced to from 60 to 50 Hz. The application requires that the operating condition considered the problem 11, the RMS generated voltage equal 13 kV line to line. As a result, the machine armature must be rewound with a different number of turns, assuming a winding factor 0.928. So that's an interesting question. When you will reduce the frequency, of course, there will be a change in voltage. Here, line voltage is given. So first you find out the phase voltage, or in our word, E phase, that will be 13 by root 3. So that 13 by root 3 is how much? It is your 10.4, I suppose 10.4 or something will come. We can check it here. When I calculated it, come 10.4. Okay, sorry, no, I must be. So it is some 7.5. So our voltage is 7.5. Right. Now this 7.5 must be generated from how it should be generated. This 7.5 should be generated. This is the RMS value. Therefore, we should multiply the root 2 to find out the peak value. That is equal to your omega. Here we can use, instead of this formula, we can use another short formula that will be very effective for this kind of problem. Is applicable for RMS value. Right. And if you have some winding factor, you should introduce them here, Kw. Correct. So what is this N? N is the number of turn. Omega is the frequency in radian per second. And you have your this phi is the flux per pole. Right. So if you calculate that, let us see. I told you the previous case, we should get some 8.24 kilovolt. Let me see what we are getting here. If we put the values, let me just check whether we get 8.24 kilovolt for this problem or not. Here, omega need to be calculated. Is it is 125. I'm trying, and I think eventually we are going to get the same answer. Into n, here, how much is your n? N is 11, right? So your n value is given 11 turn coil per pole pair. So into flux phi is how much? 0.937, I suppose. So KW, leave that KW part. So what it should give us? So now I'll confirm this formula once again. Just this formula come to my mind. Otherwise, you can surely work with this one. This one always works fine, but actually I took this problem from the book of Fitzgerald, so I need to check once the formula, and I can confirm that. But otherwise, the formula like here, as per I remember, it was radian, but when I'm trying this, it's not matching with the answer. But nonetheless, I'll confirm this. What is this omega? Remaining things I remember, it's okay. Only I need to check whether omega was in radian per second or it is in rotation per minute. Okay. Now here in the problem number this 13, all these problems I have taken from the classic book of Fitzgerald. Here, what is saying that we have our synchronous machine problem 11 application frequency is reduced. Now, what we need? We need something to thirteen kV line to line. Therefore, you can figure out the value that is so that should be 'We have to find out the required number of series turns. So what is there? Here we can write that this number of series turns An is equal to, or we can also write that TPH into your 3, but let us keep it to N. So total number of series turns here is how much? Okay, if you are getting confused, then you can check this formula, right? Here I mentioned everything. What is N? What is all these things? Now, when you have your N, we need to find out the N. So N could be find out using this root 2 to root 3, sorry, root 2 into 13 by root 3 into your omega. If we try to use this formula, and I don't here that omega into your no, omega into your winding factor into in should not be there. So k omega into your flux per pole. So once you try to calculate, it will give you some 39 turns. I'll share the the step, like this is the process how we should proceed. And once I confirm the omega, just I need to check the physical book once, and then we can come to a conclusion. You can use this formula for finding out the. But one thing I just want to tell you that you can understand this 11, 12, and 13. They are pretty simple problems, so don't expect them that this much simple problem will come in your exam. So it's better you prepare yourself for the other first 10 problems, which actually deals with a more complicated nature of the problem. Right. 14, what it says, the design of a 4-pole, 3-phase, 230-volt, 60 Hz induction motor is based on the stator core length of 21 centimeter, inner diameter 9.52 centimeter. The stator winding distribution has been selected as a winding factor this much. The armature is wide connected, thus the rated phase voltage is 230 by root 3. The designer must pick the number of armature turns, so the flux density in the machine is large enough to make efficient use of the magnetic material without being so large as to result of excessive saturation. To achieve this objective, the machine is designed with a peak fundamental air gap flux density of 125 Tesla. Calculate the required number of series turns per phase. So number of series turns per phase is, you can some book you write TPH, some book you write N, right? So they are same thing. Don't get confused that they are different. So how should we proceed? Here we can use this formula that so if you use stator inner dia, then there is no need of writing this 2. When you are talking about stator inner dia, you don't have to talk about that. So what are the information given? 1.25 Tesla. Okay, flux density, how much you need, that we have to figure out from this. How much is the number of the pole? 4 into your, here the diameter is given, so no need to incorporate this 2. B peak is 1.25. Then you have stator length. How much is the stator length? 21. And stator inner diameter is 9.5. So with this information, we can find out our air gap flux that will come around 5 milliweber. And once you find out the flux, then you can find out the pole, number of turns, which is given by which is I'm writing so many alphabets because people often ask, in this material we have this, in this material we have this, so better write all of them together. Here VRMS is 230 by √3 into number of poles, that is 4. The frequency 60 Hertz. So 60 Hertz frequency. then the winding factor, and then the flux. So once you do that, you will get 43 terms. Make sure the terms should always be an integer number, not a fraction. So that part you should take care of. Now, how to find out the L? The formula is given. You just need to put all the values. L is equal to your 4 mu 0 you should put it that how much L you'll have here. You should have 21.2 millihenry, right? So I hope only one thing will remain, that I have to confirm that formula. I will, okay, let me just tell you the formula, because otherwise things will, you people will become, find it problematic. So where is that book? Well, let me complete, then I'll write. Otherwise, it will take unnecessary time.